So this video is part of a course on food physics. This porous media framework is part of the theory section of that course, and this last part in the porous media framework summarizes the framework. The immediately preceding video sets up the governing equations for heat transport. Now, it is important to know that the transport equations that you're about to see, they look like single phase equations that we are more often familiar with, but they're averaged. How are they averaged? They're not averaged over the entire domain. They're not averaged over the entire domain like this. They're not averaged this way. Instead, they're averaged locally. Instead, they're averaged locally like this one over a what's called a representative elementary volume. So the net result is where there are strawberries, let's say here, let's say here on the left side there are strawberries, then there are brighter red regions where there are no strawberries, like here. Let me show, like right here, then that place is darker. So the original geometry, original details are somewhat smeared over. It's not going to represent the exact structure, but this smeared model as shown um, uh, on the right, and that is the nature, that is the approximation over which the equations that we're about to see are valid. So the transport equations in porous media, like this one for water, it looks very much like they look very much like transport equations for simple two-component system like diffusion in water, like this one. So for every phase, whether it's water, for vapor and air, they look very much like the one for the simple two-component system, even though these are for multi-phase or multi-component transport in porous media. However, these equations have significant differences. That's what I want to talk about a little. And so the first one is spatial averaging. They're both averaged, but the the continuum equations that we normally deal with, they're averaged over pretty much molecular distances, whereas the porous media equations are averaged over representative elementary volume, which is much larger distance over which they are averaged. So that's one difference. Then another difference is where are the velocities coming from. So the velocity in the regular transport equation comes from solving the Navier-Stokes equations or some variations of it. But the velocity in porous media, it's a superficial velocity, and it comes from Darcy equations. So the Darcy equation replaces the Navier-Stokes equations. Another one related to the velocity is how we deal with the convective term. So in the convective term, here we use concentration of the phase that we are writing the transport equation for. But here in porous media, we write density of that phase. It's because of how this velocity, the superficial velocity uw, is defined. It is effectively volumetric flux, or it's the velocity of the pure component, and so it is multiplied by the density for that reason. Then the next term is the diffusion. So diffusion then in a simple two-component system, it is often just molecular diffusion. Whereas in porous media, even though we have a diffusion term, it is, let's say for water, it is capillary diffusion or capillarity that's treated as a diffusion. Now, instead of water, if it's vapor, then vapor would be diffusing, but diffusing only in the empty space, the space that is occupied by the gas. So even though the equations look the same, each term is kind of slightly different. Its interpretation are different. This we need to be careful about. So here is a conceptual overview of the transport processes in this multi-component, multi-phase porous media, using the kind of map that we have used throughout this module. So this is a cumulative map of all the transport processes. So let's look at it. So we have mass transport, and then we have heat transport. So mass transport includes a bulk flow, of course, and diffusion like. So let's look at the bulk flow. So the bulk flow, so we are doing this whole thing in a very mechanistic way. So the bulk flow, we want to consider for different phases using their own mechanisms. So bulk flow of water would be due to gas pressure driven, or the mechanism for bulk flow of water would be gas pressure driven. Likewise, for vapor and air, the bulk flow would be gas pressure driven. The diffusion like movement of the transport, so separate from the flow, for water it can be due to capillarity, and that capillarity is we have shown that it can be treated like a diffusion process. Likewise, if it is swelling pressure driven, that also can be treated like a diffusion process. And then for vapor phase, the diffusion, of course, would be molecular diffusion, and vapor would be diffusing in air. In the same way, air would be doing molecular diffusion in the vapor. Okay. Now, in terms of the source term, for water, we have the source term that is a negative, so because water goes to vapor. And for the same reason, for vapor, we have a source term that is positive because vapor is generated as it's converted from water. So all that was about mass, and now we come to heat transport. So heat transport also has conduction, that is the diffusion part of it, and also bulk flow. So let's look at how we include them. So the phases in heat transfer are all four: water, vapor, air, and the solid matrix. The mechanism for heat transport would be conduction in all of the phases, and then heat carried by fluid transport. So I say transport because this can be diffusion part or due to flow. Whatever is the mechanism, diffusion and or flow, the fluid would be transporting, and that fluid would be carrying energy, and we have included that. And so in case of source term, then for heat, we have a negative source term due to evaporation, because evaporation takes away energy, and we can have positive source terms depending on if we are using other mechanisms of heating, like microwave heating or high pressure heating. That will provide a positive term for the heat source, because energy is being converted from other forms to heat energy. So this gives a full picture, a qualitative but a complete picture of all the phases that are taking place in transport process and their mechanisms. After looking at the qualitative overview of all of the transport processes, now we'll look at the individual transport equations in a very quick way. So the water transport equation for the water phase in the porous media is like this, and it has the convective term from gas pressure or the convective term from the gravity. Now, gravity is typically not important because quite often the food matrix is unsaturated, so the capillary pressures are much stronger than gravity. But we can have gas pressure. So those are the two that are included in the convective term. Now, the diffusive term can come from one of two that we dealt with for water. It can be due to capillarity, which almost always is there, or it can be due to swelling pressure, which is discussed in detail elsewhere. The swelling pressure, for example, as we cook meat, it holds less water and it shrinks. And this kind of a mechanism is included using swelling pressure, which in turn can be written as a diffusion term. So likewise, capillarity can be written as a diffusion term. So we have the diffusion term and the convection term, and of course I dot is the term due to evaporation, and because water is lost, it has a negative sign, and then this one of course is the transient or the storage term. Now we come to the vapor transport equation. Vapor transport can happen due to one of two mechanisms. So the flow of vapor, that can happen simply due to pressure gradient. So that's the bulk flow, or vapor can diffuse into air, which would be included in the diffusion term. Plus vapor of course has a generation term, which is positive because vapor is being generated from water, and of course this is the transient term for vapor. Okay, next we would normally expect the air equation, right? But instead of air equation, for computational reasons, we often combine air plus vapor together. So air plus vapor together, so that still gives me an independent equation because we have not considered air phase yet. So this vapor plus air transport is by flow only. So in this equation, you notice there is no diffusion term because the gas together, vapor plus air, is not diffusing. So we only have the flow term, and the flow is due to pressure gradient from high pressure to low pressure. And of course, this I dot term is still there. That's the term due to evaporation because it's vapor plus air. So I dot is a contribution from the vapor side going from water to vapor, and this is the transient term. So in the transient term, one thing we want to remind ourselves is this equation is solved for the pressure. This equation is solved to get the pressure. This term is known because it has the saturation of water, which is kind of solved from the water transport equation. In reality, of course, they're all solved together, but we can think of this water transport term, the saturation of water is known. So in this equation, we're really solving for the pressure. Finally, the heat transport equation, which is probably the most complex one or having many terms. Let's go over it quickly. So the convection part, the heat transported due to movement, comes from the fluid phases that are in the matrix, in the solid matrix. So there is water and the gas, and that gives rise to these terms. So that's the convection part. It's important to remember that the flux is due to both pressure-driven flow, like the flow, and also due to capillarity. So together, it's the transport of water that would be carrying the energy. Likewise, for conduction then, conduction will happen not just in the solid phase, but in water and gas phases. So all of that conduction is included by having an effective thermal conductivity that we have discussed elsewhere. Then the heat equation also has any heat generation term, like from microwave heating or from high pressure heating, or it also has this energy lost due to evaporation. And finally, this is the transient term. So the transient term, because there are 4 phases, the volumetric heat capacity is volume averaged between the 4 phases. So this is the effective volumetric heat capacity. So that's the heat equation. So here now are the complete governing equations for transport in porous media. So there's an equation for water, for vapor, and for vapor plus air. Water gives the concentration of water, this gives concentration of vapor, and this one gives pressure. And then the heat equation gives the temperature. Now, there are 4 equations here, but there are 5 unknowns. And so fifth equation we need, which is a separate equation for the rate of evaporation. That's not on this slide. It's important to know that these equations are for a special case. It's not the most general case. So in this case, the swelling pressure and gravity are ignored because we are talking about the porous matrix being unsaturated, which is quite often the case. So when it's unsaturated, then gravity can be ignored, and also swelling pressure can be ignored in many of these cases. So it's the capillarity that's built into this and the gas pressure driven flow that are built into this. So this is the most complete set of transport equation, but only for that special case. Yet it is it's for special case, but it is still applicable to the great majority of food processing situations. Now it is very important to realize that these equations are strongly coupled, and coupled in more than one ways, but one of the obvious ways it's coupled is through the evaporation term. So water loses water, water is reduced due to evaporation, so it has a negative I dot term. Vapor is increased due to evaporation, so it has positive I dot term. For the same reason, we have I dot in the vapor plus air equation. And then energy equation also has the I dot because it has to include the latent heat of evaporation. So this evaporation terms couples these equations in the most explicit way. So now a little bit of comment in a big picture way. What we just finished are the derivation of the transport equations for water, vapor, air, and energy in porous media. So what's next? Now recall that evaporation I dot, we really didn't get into the details. So that's in a separate module. So these auxiliary conditions would be the next thing to learn, and one of them would be the evaporation term I dot. How do we get that? Then we will have to learn about the boundary condition. We have not talked anything about that. And then moving on, if you want to use microwave heating, for example, those are discussed in separate modules. So those auxiliary conditions would be the next thing to learn. So continuing on in a big picture way, what is next to follow? So if we want to be more realistic, then we know that food almost always shrinks due to loss of water or expands due to gas pressure. So there's change in the size. So we have to include that if we want to be realistic. We need to include this deformation, shrinkage or swelling that can change the transport processes substantially. That's why we have a module on poromechanics that combines the transport with the mechanics part. So the details of modeling deformation are explained in that module, and that would be an important one to include if we want to be more realistic in terms of modeling the food processes, because there's always shrinkage and swelling. This is the concluding slide for the entire transport section, that is this module. We note that those transport equations combined with the equation for evaporation, that's in a separate module, and then boundary conditions and any other modes of heating like microwave heating. Those are in separate modules. When we combine all that, we get an unprecedented mechanistic look at what is really going on in a process. That is not possible in any other way. So here is an example. So this is a simulation of microwave drying, where we could look at how the dimensions change, how the pressures develop, how the temperatures develop, and how the moisture develops, all with space and time. So it's very rich in its information, and it provides us with an unprecedented level of understanding. And what does that do? By knowing more precisely, we can optimize and thus speed up product and process design in food industry.